So can you tell us more? Can you tell us about who you are?
Sure. So I'm Shreyas Narsipur, and I am currently an assistant professor at the Mississippi State University. I just joined here probably like in the fall of 2021. Prior to this, I was a teaching assistant professor at the North Carolina State University and also the director of the aerospace labs there, where I would do teaching and research in the subsonic wind tunnel, supersonic wind tunnel, and the anechoic chamber. But my main research area or focus is in applied aerodynamics, where what you look at is, we look at all the, the flows over different geometries or different bodies, understand the flows, understand the physics of those flows, and try to model them. And we use both experimental as well as computational tools to understand the flow physics, and then try and model them in methods for fast design analysis purposes.
Mhm. So why did you want to become an aerospace engineer?
Well, simple answer is I love aircraft, right? So I think the first time I flew was back when I think I was 5 years old. I was traveling. And since then, I was always in love with aircraft. In fact, my first idea was to become a pilot, right? And well, I got my glasses. I mean, of course, not that stopping anyone now. But then, of course, that was one case, and the other reason was that I felt like, after coming from a family of engineers, and my granddad, right, was an aerospace engineer too at in India. So he kind of used to always influence me, keep talking up, all the stuff that he used to do in his work, and that really pushed me to become an aerospace engineer. So yeah, love for aircrafts from the very beginning, and kind of converting that my passion into a job was, I think, the best decision I ever took. So
Mhm.
that's why I'm here.
So can you explain some of your work in experimental aerodynamics?
Sure. So yeah, like I said, my field is in applied aero, where you can either use computational and experimental tools, right, to analyze flow physics. So currently now, a lot of my work when I was doing my PhD and a little after too was more based on using computational methods, right? But I've always been interested. I like doing hands-on, right? So I like doing practical stuff. So experimental aerodynamics was the way to go for me, right? So what I do in experimental aero is at Mississippi State University, I run the subsonic wind tunnel over here, based on the experience that I already had. And there, what I do is I build models to test unsteady aerodynamics. So this is when with the application of when aircrafts actually they fly, they flutter, right? They start to move up and down. So that time you don't go into steady anymore. The aerodynamics are slightly different, and that is not really well understood, right? So we I do testing with that. Another area that I look experimentally look at is prop wing interactions, right? So you have these small UAVs that are driven by these small propellers. Now, propping interaction was not such a big deal when the aircrafts were a lot larger, because the propeller, the aerodynamics of the propeller was not really affecting that of the wing. But now with smaller UAVs and smaller aircrafts, the propeller interactions actually matter. So I'm trying to experimentally understand fundamentally what's going on, right? With that, and trying to, decipher what the fluid mechanics are, what the aerodynamic and how the fluid mechanics affect the aerodynamics and the performance, right? Uh, and then kind of translate that to, number one, providing the data out there, and second, using that to build the low order methods that are what on what I like to do, right? That's kind of my one of my research focuses. So yeah, so unsteady. So long story short, unsteady aerodynamics, experiments on prop wing interactions, right? And also, testing small scale UAVs for performance, aerodynamics, and more recently, looking at even the aeroacoustics, right? So put them in a wind tunnel, run the propeller, and see what kind of noise is being generated out. Those are the different experiments that I kind of I work on as part of my research.
Mhm. So can you also explain some of your work in some of your studies in acoustics pertaining to aircraft?
Sure. So yeah, so my focus is on prop aeroacoustics, right? So now if you have anytime you've flown a drone, right? These days, drones became really big in the past, 10 to 15 years. And these days, anywhere you go, and drones come in all sizes, right? But one of the biggest issues with drones is the noise that, you're flying a drone, you're, even like, mile away, you can hear the drone coming, right? So the issue with that is, and that has to do with, acoustics is essentially connected to the pressures that are, the propeller slipstream and all the pressures that are being caused due to drone flight, right? So, so the same pressures that you use to evaluate the aerodynamic characteristics are also used to even evaluate what the acoustic sounds are coming off. So the idea is the drone we are trying, or in my experiments, I'm trying to figure out what is the best kind of balance between, having the good, maintaining good aerodynamic performance while keeping the sound low, right? The sound levels low, because especially when you try to go now these days, people are talking about urban air mobility, right? Where they want air taxis and, all of that good stuff. And on the, in the military and army, the military research side, they want something to be quieter, right? For different
Yeah.
operations, whatever it is. So how do you make things quieter while keeping the performance at the same level? And this is, I'm more specifically focusing on smaller propellers, and trying to, using experimental methods, figure out how does the different things, right? How do the propeller slipstreams, that is, the wake because of the propeller, affect the aerodynamics and the acoustics, and what can be changed, right? In order to get a good balance between that, where you have more acoustically, they're quieter propellers, as well as aerodynamically, they are performing at the same level that you want them to be.
Mhm. What are some of the things that you're working on in the area of flow control?
Yeah. So flow control is again another. So a lot of my PhD research or research previous to this was in prediction methods, right? So what essentially we do is, like I said, in applied aero, you figure out the physics of the flow, and then we do something called. And my area was also in low order method development, right? So what we do is we understand all these physics, and then we augment these basic fundamental methods, right? We call them implicit models. They're ideal models, right? We augment them to simulate viscous effects. So essentially what you're doing is you have computational aerodynamics to do that, but computations take a lot of time. They're very expensive, right? So you want a tool that can do these things a lot faster, right? With good accuracy. So that's what low order methods are. They are much faster than your computations, and I mean definitely they lack a little bit in accuracy, but at least when you're doing design processes, you can actually do it a lot faster, right? Which then you can then, and whatever design you down select, you can then go to the the computation and then the experimental side of things. So I was working on building these prediction models. So I've got models that can, and I was mainly focused on unsteady aerodynamics. And these models now, the final model that came out of my PhD was it did a very good job in predicting the unsteady aerodynamics of an airfoil, right? Of wings and airfoils. So what I'd like to do now is my work in flow control is more focused on how do I take these prediction methods, because they're so fast, right? How can I take them to actually control the aerodynamics or control the flow, right? So what I'm trying to do is we had methods in which in unsteady aerodynamics you have these vortices and all of those vortices that shed out of the wing. Uh, so sometimes having the vortices is good, sometimes it's bad, right? It depends on what state is in. So my flow control work is now using my prediction models can predict how the vortices will behave. Now using that prediction, I'm going to do an inverse design to figure out how I can control the vortex shedding and all of that to get to enhance my aerodynamic performance.
And also, what are some of the improvements you're looking forward to in the area of propeller wing aerodynamics?
Yeah, so it's a good question. So in prop wing aerodynamics, right now, my focus is on low speeds, right? Like low velocities, or what we call low Reynolds numbers, right? Because that's the region. There's a lot of data on prop wing interaction when you look at much higher flow velocities or high speeds, right?
Mhm.
But like drones and UAVs and all that are relative. It's a lot new. It's much newer, right? So there still needs to be a fundamental understanding of what is going on with the prop wing aerodynamics, right? What does the flow look like? How does that flow, how does the propeller flow affect the flow on the wing, and how does all of that affect the aerodynamics and the performance, right? So what I'm hoping to see is we're going to start from basic models, figure out, what the flow characteristics are, understand the flow dynamics. And once you understand that, then we can start informing how you can make these designs a lot better, right? And that's where I see. So the idea is get a fundamental understanding and then figure out design methods that can be applied to make a prop wing system a lot more efficient than what it is based on what we understand, and also use all of that, use all the data that you collect to again build low order methods to be able to predict this, so then it can be then used for control purposes. So that way closing the loop between you know understanding, prediction, and then control.
So, what's been your toughest accomplishment so far in your career?
Toughest, so that's a difficult question, right? So to be very honest, every stage that I've started right now, when I was, from an undergrad student to a grad student to a PhD, right? Even now, even in my recent job that I joined, it'll always be very tough, right? Or it looks really, really tough because you always feel like, hey, there's this huge task, Herculean task in front of you that you have to kind of, face, right? But I think for me at every stage, whether during the start of a lot of stages, right, whether it be, there's that excitement there, but also there's that difficulty of it, right? But what I've realized is as long as you have an open mind and you're able to give it your 100%, you start to enjoy these things, right? Because first of all, you're here because you enjoy doing it, right? And at that point of time, honestly, nothing is too hard to handle, right? So yes, I did feel so. I think at every stage, one example being my PhD, right, when I started, I really felt like I had no idea. And it's there, right? You are here to learn, right?
Yeah.
But I think if you keep that right attitude, open mind, and give it that, give it your all, I think by the time I finished my PhD, I had that feeling that I knew I deserved to be there, right? I knew I deserved what I was doing, and so things. It was not really. It personally, yes, it was very satisfying, right? But I think the tough part of it was probably in the start of it, but you kind of get over it as with tenacity and just like 100% work.
Mhm. So, to high schoolers like me and to younger generations that want to become aerospace engineers, what would your advice be to be successful in this career?
Focus on your basic physics and math. As long as you are within the atmosphere, right? You're using Newton's laws, right? The three
Mhm.
laws. So one of the things that a lot of high schoolers and all, when you guys come into engineering, engineering is, it's going to be fast, right? I mean, you're going to start learning, you know, different areas, right, within 6 months, right? But essentially, all of it stems from your basic physics and math, right? So focus. My advice, and also the other point is you now have from high school all the way to all of high school pretty much, right? To focus, to really learn those basic concepts, right? If you're able to get a good hold of those basic concepts, right, where you have 3 to 4 years to learn all of this stuff, engineering, you'll have 6 months to apply all of these concepts, right? So my advice to all high schoolers is you don't need to do create. I mean, yes, it's good to do like AP physics and all of that stuff. It definitely helps, but I would prefer you understanding your basic physics and math to a very good degree, so that when you come into engineering, they are just applications of these problems, right? So when you have a problem, it might look tough at the beginning, but if you're very strong with your basics and you break your problem down, you can always build it up because your basics or foundations are very strong, right? So focus on basics and math, practice coding, right? That is so important because you can't get away from it. You can be a mechanical engineer in aerospace or whatever. Coding is something that is a very, very important skill set to learn because as engineers, right, when you get a job and all of that, you are, or even you're studying or you want to spend your time analyzing data, right? You don't want to be spending time trying to process data or collect data, right? These things should be done automated, in an automated fashion. Once you set it up, it has to keep going. And you should process your data also. It's pretty much you'll come to a point where the data that you're seeing is always, you'll see a lot of data that has to be processed the same particular way, right? So if you're able to automate all of that process, then you are spending more time analyzing that data, right? That way, when you analyze the data, then you can figure out what is wrong with it or what's right with it, and then go back and get that loop a lot faster as compared to that. So that's the second. And finally, learn the art of Googling, right? Everything is available on Google these days. You do not, any equation that you need, whatever it is, it's all available. You just have to know where to look for it, right? So don't feel that, oh, the answer should be readily available or there should be a book to do that. Everything is available online. That's one of the ways I learned coding too, right? I was not, I mean, I knew the basic stuff, but like coding, like MATLAB and all of that, everything I would Google, learn. And because of that, I'm able to find answers. I'm able to make my process a lot faster. And by understanding my basic physics and math, I learned this a little later, but if you know that basic physics and math, no engineering problem is going to be a big deal for you guys.
Mhm. Well, thank you for joining me, and it was really nice to interview you.
Sure. Thank you so much. Appreciate
All
it.
right. No, have a great rest of the day.